Welcome to another podcast. This episode, we're going to be taking a look at the second fundamental theorem of calculus. The previous fundamental theorem helped us evaluate definite integrals. This fundamental theorem is going to introduce a new function to us called the area function. So let's just start off with the theorem itself, and then we'll talk about some of the new things that this is going to add to our repertoire. If the function f of x is continuous. So this only applies for continuous functions. So if f of x is continuous, and we know that the function a of x is equal to, so we're going to define the function a of x to be equal to the integral from a to x of f of t dt. And this is where t ranges from a to x, then I can easily say that a prime of x, the derivative of this function, is f of x. Now, it may seem a little obtuse. It may seem like you can't get your head around what we're talking about here, and rightfully so, because there's a lot going on in this description. First off, let's talk about this function that we've created here. So a of x we've defined as the integral from a to x of f of t dt. First off, let's give this a name. This is called the area function. And to figure out why this is called the area function, let's take a look at the graph or the figure that goes along with this. So get a curve here, drawing some axes. And so let's suppose that we have a function f of x. We're going to go from a, and our function does all sorts of things. And we're going to go, say we're interested in the integral from a to b, but we want to look a little bit at a time. So we want to go from a up to x. So we're gonna calculate this area for different values. So this would be the integral function. So as x moves, as x changes, the area added up changes. So I can consider all possible values of x between a and b. So a at b would be equal to the integral from a to b of f of t dt, which would be everything here. A of a, there would be no area. So this integral would be 0, because if I started at a and never got off of a, then I wouldn't be adding up any area. Another thing that happened here that may be causing you some problems is, up till now we've had f of x dx in our integral. So what gives? Well, because I'm using x to represent how far out we're going to calculate the area, then I can't also use it here. Because remember, this thing right here is the width of the rectangles. It's sort of the infinitesimal width of the rectangles. Now, the way that we should interpret this is that I'm just giving that a name. So I called it delta x in a previous video. I'm just going to call it delta t or dt this time. Makes no difference what I call it. What you need to understand as the student is the width of the rectangle should have nothing to do with this x value. Just because this is the distance over which I want to calculate the area doesn't mean my rectangles have to have width dx. This x doesn't have anything to do with this. We call t here. So this is sort of the new concept that's being introduced here, or one of the new concepts that's being introduced here, is t is a dummy variable of integration. Or probably a better term to use for those of you that are computer science folks is t is a local variable for the integral process or you can think of it as the integral algorithm. right? So if you think of the algorithm of the integral being those three steps we introduced earlier, namely divide it up into rectangles, sum up the rectangles, and take the limit, that's sort of an algorithmic process. T is the local variable that describes the widths and the positions of the rectangles. So in a programmed sense, a local variable is a variable that's only used for the machinery of the algorithm, and the output has nothing to do with it. And that's sort of the case here. The output here is a function of x because it depends on how far out x I go, and t gets lost sort of in the shuffle. And so I just want you to understand that it is inappropriate to have a variable in the limit that matches the variable in the integrand. So a couple of new terms here. This is the limit up here where the x is, and this function here is often called the integrand. And so it's inappropriate to have the variable of the integrand match the variable of the limit. That's going to cause you all sorts of problems in Calculus 2 and Calculus 3 where we have multiple variable situations. And so you should be very careful about where you place your variables and how you interpret those variables, because even if you mean well and even if you understand what's going on, you can get in situations where you can be completely confused by a mistake in that regard. All right, so we actually haven't talked at all in this video yet about what the fundamental theorem of calculus says. So let me kind of give an example to sort of illustrate this. Basically, the fundamental theorem of calculus, the second part of the fundamental theorem of calculus, says that if you have a continuous function, then the derivative of the area function is f of x. Or, maybe stated in a different way, it simply says if I take the derivative of the integral from a to x of f of x, or see, look what I did there. I used x in both places. F of t dt, if I take the integral with respect to x of that, then the answer is f of x. And how you interpret this as a student, at least right now, is the derivative and the integral cancel each other, and the x in the limit becomes the variable in the function, and I have f of x. So just as a quick example of this, suppose I asked you what is the derivative of the integral from 1 to x of the function 1 over t squared. So get used to this notation as well. Sometimes we put the dt up here. I could also write it as 1 over t squared dt. This means the same thing. So the answer is, what is that going to be? Well, by the second fundamental theorem of calculus, so FTC2, the derivative of the integral cancels, and I get 1 over, replace the t, the dummy variable, with x, I get 1 over x squared. So that's my answer. Well, great. Let's see if this is consistent with FTC1, so the first fundamental theorem of calculus. I'm asked to take the derivative of the integral from 1 to x of 1 over t squared dt. So up here, I didn't calculate, so this required no integral calculation at all to be able to do this. So the fundamental theorem of calculus says that if I was faced with this problem, I would do the integral first, and the antiderivative of 1 over t squared is what? Well, 1 over t squared is t to the negative 2, and I know that when I take the integral here, by power rule I get negative 2 plus 1 over negative 2 plus 1, which is negative 1 over t. So I know that this is the function negative 1 over t, and I'm going to evaluate it from 1 to x. And so keep in mind that this 1 to x is evaluated from t equal 1 to t equal x. So I'm still not done with that intermediate dummy variable yet. All right, so this is the derivative with respect to x of negative 1 evaluated at the top, so negative 1x, minus evaluated at the bottom, it's negative 1 over 1. So this is the derivative with respect to x of negative 1 over x plus 1, and the derivative of 1 is 0, and the derivative of negative 1 over x is 1 over x squared. And so we see that the two matches up in both cases. So the second fundamental theorem of calculus is consistent with the first fundamental theorem of calculus, but the added advantage is it allows us, in the case where you have the derivative of an integral, or more specifically the derivative of an area function, it allows us to forego integration altogether and simply replace the dummy variable of integration with the variable for the area function. And so this is the fundamental theorem of calculus part 2, and it's the last of our fundamental theorems that we're going to have in this course. Keep in mind some of the new things we introduced here, specifically some of the new notations, talking about dummy variables and area functions, talking about integrands versus limits and the differences there. Those are some of the important things to come out of this discussion. All right, thank you for watching.